My name is Vasily Sardakov, and I would like to present you the EActors framework. The first question which I want to try, which I want to try to find is why do we need another framework? Because we have a lot of frameworks, why another one?
Could you speak up a bit, please?
Sure. So, just for recap, Intel SGX offers new system components, so called enclaves. Enclaves are part of user space applications, and they are isolated from, and the code and data of enclaves are isolated from that of other enclaves. So an enclave can, let's say, code from enclave can access data located in ring 4 inside the application, but cannot access data and code inside another enclave. And enclaves are protected from attacks based on physical access by the use of encryption of physical memory, removes the operating system and the hypervisor from the trusted computing base, and offer very interesting features like local remote attestation and data seeding and more. Intel offers Intel SGX SDKs. This SDK provides you necessary primitives to program enclaves, and they do this in a very straightforward and easy way. So you can create a function and decorate it in a special way, then compile the function together with the Intel SGX SDK, and SDK generates a binary or multiple binaries of enclaves and glue code which allows to start or deploy enclaves. And this is a very intuitive use, so it's just an RPC-like manner of programming of enclaves. However, there is a problem. To enter into enclave, you need to perform something called OCall. So there are mechanisms for switching between untrusted and trusted execution environments, and thus transitions are very, very slow. Compared to ordinary system calls, switching between trusted and untrusted 50 times slower, and more than 50 times slower. It's only for the beginning. And you will need to leave your enclave very, very soon, because inside enclave you cannot directly interact with the kernel. So if you want to interact with the kernel or use a function which is not located inside an enclave, you need to leave this enclave. Again, 50 times slower. For example, you have two threads. Those two threads need to pass a critical section. They need to use mutexes. Mutexes require the involvement of the kernel. Both threads need to leave the enclave. We have more than 200 times slower synchronization mechanism compared to ordinary mutexes. So it's very, very slow. As a response for this issue, researchers provided several frameworks. Frameworks like Heavens, Con, Graphene SGX, SGX LKL, Panoply, and maybe some other. So more than 5 different frameworks, and they follow same and different approaches at the same time. So you don't need to leave an enclave if you can do everything what you need inside an enclave. So for example, you can emulate some unavailable system calls inside an enclave, and therefore you don't need to leave the enclave. And various projects abstract different layers of the software stack. So someone abstracts the libstib interface. Another project abstracts let's say the kernel interface. But conceptually, those frameworks have problem. It's a monolithical design with a very huge trusted computing base. So, and this is a kind of irony. You wanted to remove the complicated kernel from the trusted computing base, but to run your legacy application, you anyway put parts of the kernel inside this trusted environment. So, large TCV is the problem. However, there is another way, and a single host or a single process can host multiple enclaves, and this is a very interesting feature of SGX enclaves. Inside the one memory isolated environment, you can put multiple, you can put multiple enclaves. So your program can consist of multiple mutually distrusted components located inside different enclaves. What application can be? For example, you have a message server like XMPP server, and you want to make group chats. You can put one group chat inside one enclave, another group chat another enclave. so they will be protected, and in the case of intrusion, this data will be protected, obviously. And at the same time, since it's the one single service, clients should have a mechanism to interact through enclaves. Another example was considered by people from Microsoft. Thank you, very nice example. Multi-party computation. When you have multiple mutually distrusted binaries, but those binaries which belong to different owners should perform mathematical function or find a consensus or make a decision together without exposing of internal values. In a simple case, you have several isolated parties. Each party is located inside an enclave. For example, this enclave has a secret value inside, and three parties should perform a mathematical sum without exposing of open values. So for that, again, you need to have multiple enclaves. You need to have a mechanism for interaction between them. And at the same time, it should be one unique application, but not a distributed set of isolated or distributed set of different applications. And to implement such applications, you need to have a programming framework, and you need to have necessary system support. And I think the right way is to do this by the applying of the conception of actors, because actors conceptually are not blocking entities, and they follow the conception of no sharing. So you don't need to involve synchronization primitives. So you don't need to leave an enclave. You don't need to develop mechanism for synchronization within the enclave. So it's very easy. So they don't use logs. And conceptually, they're very lightweight, so it's very nice from the point of view of another problem related to SGX enclaves. It's an EPC problem, so there is a problem of paging if the size of all enclaves reaches, let's say, near 92 megabytes. So, actors. And of course, there are many actor-based systems, and the problem that they're very heavy. It's very complicated. Well, it's not very complicated to port, let's say, Erlang VM into SGX. The question is, what overhead will you have if you port this? So we can use, but with very high overhead, Erlang, Java, and conceptually, those frameworks are not tailored for trusted execution environment. So yes, you can run it, but they are not. They don't use features of enclaves. And that's the reason why I decided that we need another framework, and I will present it today. So it's EActors is an actor-based framework, as many other actor-based frameworks. To describe it, I will answer three questions: what an actor is, what is an actor, how does actor communicate, and what system support the framework provides. This figure shows a general view of the actor of an application written in this framework. So there are several enclaves, 1 and 2, and there are actors. They are called EActor it's a notion of an actor in this framework. So there are 4 actors, and 2 actors are located inside one enclave, 2 other actors located in another enclave, and there are workers. Workers technically are p-threads, physical threads, that provide execution context for actors. So actors itself are passive entities, and they can act only if they have execution context. And there are bindings between actors and enclaves. For example, you see 2 actors inside this enclave, 2 actors inside this enclave. Workers to CPUs, it's a CPU affinity. You can say that this thread will be attached to this CPU. That can be very useful from the point of view of performance and optimization. And actors to workers. As I said, workers provide execution context. To create this application, you need to have the framework, the source code of your actors, and the XML file that describes the deployment scenario itself. So the number one aim of the framework is to provide the very simple tools which help you to build a very flexible application. Today, for example, you want to put all actors inside one enclave. Tomorrow, let's say you want to have 5 different enclaves, and the switching between actors, between enclaves, should be very, very easy from the point of view of the developer. And deployment scenarios are encoded in or are stored inside an XML, while you don't need to fix the source code of your application if you want to change the deployment. The framework itself generates binaries of enclaves. So, for example, if you have 5 enclaves, the framework will generate you 5 different enclaves, and each enclave will have only used inside this enclave source code of actors. So they're very lightweight without unnecessary code inside. And this is a very simple application. So there is a constructor for an actor. So this constructor usually initializes communication interface between other actors, and the actors. This is the body function of the actor. So by definition, an actor can interact with other actors only by messages. So actually, what's going on? We receive or send message, and we react. This actor reacts if this actor receives a message PONG from another actor. Question number 1: how does actor can interact with each other? And they use nodes. It's an abstraction which describes. It's a fundamental abstraction for messaging. So it's a part of memory, and this part of memory can be trusted, located inside an enclave, or can be untrusted, located outside an enclave. It consists of 2 components. There is a header and there is a payload. So there is payload, is memory for data, and there is a header. Header is used to enqueue multiple nodes into queues. And all nodes are located at the start, so it's part of the framework. The framework provides API to deal with those queues, so very obvious. Double linked list with LI4 and FI4 interfaces. Synchronization of nodes are protected by the use of hardware local lesion. It's a very high performance synchronization mechanism without any side effects. Without any side effects. This primitive can be used by multi-producers and multi-consumers. So you just have a queue, you have set of actors that can write to this queue and set of actors that read from this queue. Let's consider an example. We have 2 actors, ping and pong, and they're located inside different enclave. To send a message from enclave 1 to enclave 2, the first actor should have access to pool of empty messages and to mbox abstraction. So firstly, ping needs to dequeue an empty node from the pool, and after that, the first actor will get exclusive access to this node. No one else can read and write it, and even access or refer somehow. Then that actor can write data inside this enclave, inside this node. Then this node must be enqueued into an inbox. So data, by the way, can be encrypted or non-encrypted. Should be enqueued into inbox, and at the same time, the second actor tries to dequeue messages from the same inbox, and succeed, it will get success. It will get exclusive access again. Safely read data inside that enclave, decrypt it if it's necessary, and then it needs to return used node back to the pool. So very simple, and this abstraction can be, as I said, can be used by multi-producers and multi-consumers, but by default, communication are not encrypted. So because of multiple reasons, and the framework provides more complicated abstractions on top of this very simple interface. Those abstractions are called cargos and connectors. And they provide encrypted, can be encrypted and non-encrypted with absolutely the same interface. So, for example, today you have 2 actors. You place those 2 actors inside an enclave, and obviously you don't need to use encryption because those actors are protected by SGX itself. So therefore, you don't need to spend time to encrypt it. But tomorrow, let's say you want to create 2 independent enclaves, put 2 different actors into different enclaves, and obviously you need to have a mechanism for which you encrypt your messages. And cargos connectors offer this abstraction. So with the same source code, just by switching 1 or 2 source line of code, you can turn your non-encrypted messages into encrypted messages. However, of course, there are it's not for free, so this interface can be used only by single producer, single consumer, peer-to-peer form. But the framework offers mechanisms for remote, for local attestation during the key exchange procedure. So if you have, let's say, 5 enclaves with 5 different actors, and those actors have 4, let's say, independent communication channels, the framework will generate necessary glue, necessary checksums, which will help you to establish encrypted connections by the use of local attestation. What else? The framework offers several system components because you cannot use, well, you shouldn't use equals inside an enclave, and therefore you need to use messages to get access to system components that are unavailable inside the enclave. For that, the framework offers system actors. They are untrusted, they're working outside enclaves, and they interact with all other actors by the messages because it's an actor-based framework. So, for example, and those actors implement mechanisms, so that can be a system call for read, for write, for pipe, for interaction with pipe, read, write to the file system if you want. So it's just mechanism. And you, for example, if you want to open a file, you need to send a message. This actor will perform this mechanism. It will open the file and send back file descriptor. So the same system actor can be simultaneously used by multiple other actors because it doesn't it doesn't have a state. Another thing, so now we can have access to any hardware from our enclaves with the same interface. But anyway, sometimes you need to have a mechanism to store data inside an enclave without share the state. It sounds a bit strange. I will explain. So. Conceptually, actors cannot have state and cannot have access to shared entity. But at the same time, instead of saying, for example, you have one message and you need to send this message to, let's say, 5 or 10 actors, and since this message is absolutely the same, sending 5 or 10 sequential messages is inefficient. So in actors-based framework, there is a conception of object store, which is not a store as a shared entity. So you may consider object store as a set of queues, a set of persistent queues, where you put data into this queue, but this data can be accessed by or written by multiple actors without any problems. So the framework offers the EActors object store. Technically it's an atomic key-value store. It can be private, it can be public, so it's not an active entity, it's a set of APIs. A set of APIs that can be invoked by actors. So any piece of memory, if it has a necessary size, can be turned into object store, and actors who has access to it can read and write to this store. Also, this store can be persistent. For example, you can map a file into untrusted memory and turn this mapped memory into an object store. So it will have persistence on demand. That's all regarding the design. The question which I want to show you the answer later is to show you how fast is the communication primitives, because the original motivation was we want to omit the use of equals and ocals, and for that we use asynchronous messages. How fast are they? For that, let's consider two actors located inside different enclaves. And in this case, they use equals to leave an enclave to send the message to another one, and messages used by and boxes used by 2 different actors written on top of the framework. So it's very simple ping pong example with 1 million messages. With those messages have different size, starting from 16 bytes up to 1 megabyte, half of a megabyte. 2 threads, so there is thread 1, there is thread 2, everything is honest. Again, different threads, just the same actors, just different synchronization mechanism. This is the performance of the SDK. As you can see, there is a pike which is near 32K. It's exactly size of the first line cache. Because when you transfer message from trusted area to trusted by the use of O-calls, there is a marshalling mechanism which copies data from one memory to another. And obviously, if this memory fits into the L1 cache, this works very, very fast. So this is the end of the cache, and it has, let's say, steady layer after 128K. And this is the performance for EActors. So much, much faster. Very fast. And because I was using in this example cargos, so as I said, you can very easily switch a cargo from encrypted into non-encrypted form and vice versa. This is the performance for encrypted cargos. So even encrypted cargos are approximately 3 times faster than non-encrypted equal-based messages, and the difference between non-encrypted cargos and equals approximately 30 times. So this interface is very fast, and you can write very, very high performance application on top of this framework. Sources are available. You can check if you want. There are several examples here. There is a template which shows an ordinary Hello World application. There is a set of various ping-pongs that use encrypted, non-encrypted, cargo-based and non-cargo-based messages. Also, there is network version of this ping-pong application. And there is a huge set of various forms of local attestation, Diffie-Hellman, and something else. So at least there's 3 different ping-pongs which use different mechanisms to establish an encrypted connection. Also, there is an example for secure multi-party computation. It's a secure SUM, or SUM, the EActors object store, and there is an HTTP web server which provides SSL connection. Yes, unfortunately this address is wrong, but there is a service primat. .ibr here should be primat. It's the title. It's a group site. It's a site of our group, and this site is hosted on top of the framework. So it shows how exactly you can terminate SSL inside an enclave, and how you can write a HTTP-based application on top of this framework. Let's talk about future plans. Because this project was a kind of a research project, it's written in C, very safe language. Obviously, you may ask a lot of questions about the applicability of this framework in general. And one of the primary problem is how to make the programming language and environment more, let's say, more safe. So currently, I'm working on the hardening of the framework. Here will be instrumentation mechanism provided by LLVM, which will limit of memory that can be accessed by different actors. So at the end, this mechanism will help solve problems related to uncontrolled access to memory by the C language. Mechanisms for partitioning, because the framework provides mechanism for easy deployment, and obviously it will be nice to have a mechanism to self-deployment or self-partitioning of actors, because actors are independent, that they can be split without or partitioned without any dependencies and problems. So this is another direction of the work. Of course, multi-enclave applications. So the framework was developed to give a tool to build such multi-enclave applications. The HTTP server will be improved. It will support multiple domains, and there are some additional ideas related to IoT. And currently the framework relies on the Intel SGX SDK, which is not very good from performance, from security point of view, so probably we will try to remove this legacy. So, thank you very much. Questions? Yes, please.
So you compared yourself against the SGX SDK, but the SGX SDK also nowadays supports switchless
Yes.
codes, and they are more performance than doing roll call all the time, right? So how does it compare against this?
I cannot give you numbers, but conceptually, all asynchronous queues, asynchronous called by SGX SDK, this interface, they absolutely, I mean, conceptually is the same. You have two threads, one thread inside the enclave, one thread outside the enclave, and there is shared memory which is used to enqueue and dequeue data. So it will be the primitive, as a primitive, it's near the same. As implementation, well, I cannot compare with switchless calls, but there is no many things that you can apply. So you can use atomic instructions, you can use hardware localization, and you can use nothing else. So maybe two approaches, and spin locks. So 3 different approaches. So they near the same performance, actually. I mean, they scale differently, but conceptually the same. So you can assume that switchless calls has near the same performance. Yes, please.
I work on a project called EActors, which is also using these, but I'm interested in some of the differences in what you're doing. This doesn't have anything, you don't do anything regarding attestation of the C, right? You leave that entirely to the application, because that's one of the hard bits, is making sure that you're talking to the actual genuine hardware and not something that's being emulated. And so in the usual model, one application needs to test before it's loaded. In this case, because you have multiple actors, how do you envision that? Is there something that each separate actor is going to do attestation on their own? Is there an attestation for the overall block of them?
So the question is how local attestation works. I will paraphrase this if you don't mind. So the framework provides primitives to create encrypted channels by the use of local attestation. And during the compiling phase, the environment generates signatures, so a mirror enclave, if you know what is it, signatures of each enclave. And you need to have, let's say, the root of trust. So one enclave that includes all mirror enclaves signatures inside. So it's a sequential process. There is a root of trust, there is the first enclave. This enclave has a set of all or maybe subset of enclaves or communication channels, and then you establish 1, 2, 3, 4, 5, let's say, and sequentially they perform local attestation. So of course it's cannot be very general approach. So currently it's tailored for sequential initialization of enclaves and sequential generation of encrypted channels. But this environment significantly reduces the complexity of this procedure. So if you can map your application to this design, so like you can sequentially establish connections between several enclaves, yes, you can apply this framework immediately, and the framework will generate necessary paths. Otherwise, you will need to create, let's say, a zygote or something very initial, very root of trust, and this root of trust will establish connections between different enclaves. So this will require you to modify the framework. Yes, please.
Well, just said the word identification. So what about the namespace problems? How do these guys actually know about each other? And that's related to the question of object store, which always was a bit of a problem in parallel architectures with virtual machines and so on. Somewhere you have a repository, and this has to be managed, and it tends to become a big mess because someone has to look after this. So do you solve all these problems by being stateless? How do you get rid of the messages once you deploy these 5 entities to your consumers?
Very, very good question. The question is, what about namespace inside the network, inside the framework, to distinguish different actors? And I would say no, there is no mechanism. There is no mechanism for that because you are absolutely right. So name discovery, so mechanism which maps actors to unique names, well, would be is very complicated in general in distributed systems. So in the framework, there is a mechanism for naming and identification of actors at the source code level. So a tool that generates binaries knows something about source code of actors and their names, but there is no independent mechanism for name discovery. Your question?
I had a very small technical question. So you had a graph where you showed the L1 cache, right? I assume this is on more recent Intel processors where you do not put the L1 cache on enclave entry?
I wouldn't say that it's very recent. So this diagram, let's say, 2 years old.
Because, yeah, so then it's either old, because now we're in a situation where on current Intel processors, due to the microcode updates, you need to flush the L1 cache. So your entry and exit events become even more expensive, basically.
I would say that each microcode update cuts performance. Very, very significant, I would say. So this is the problem of updates.
So maybe as a, let's say, high-level opinion question, do you think it was maybe a wrong design decision to have an initial SDK where entry and exits are basically modeled as operating system level system calls, and you see that operating systems, both in software and hardware, have been highly optimized for fast system call entry exits, and with enclave you see exactly the inverse. Every time we learn more about this, it becomes more expensive to enter enclaves.
The question is, is this the right way to use messages instead of e-calls? At the beginning, I did not consider. So at some moment, for some applications, I thought that the use of e-calls is okay, but now I don't think so. So I still believe that, and I see this in numbers, that asynchronous interface is much better. However, it has significant drawback because you cannot stop a thread inside the enclave, and this thread anyway will need to leave the enclave at some moment. So, and which means that anyway, at some moment, for some reason, or due to the reasons of scalability, any of my thread will leave the enclave. So in some form, OCall still exists, but the programming model doesn't rely on this. That's the important. This is important. Yes, please.
Time for another question?
Please.
Okay. Well, first of all, we can stick to the message model. So access is king. But sorry, I have to interrupt you. Forgot the question.
How much time do you have?
No, just to take from
Around 34. So.
Oh yes, I got it again.
Yes, please.
So, well, these problems of multi-party computation are typically solved by using multiple physical entities that people really distrust each other. So everyone has his own machine or virtual machine, and then got message party back and forth. So what you're suggesting is actually bring all to one single CPU, and therefore get more efficiency because stuff is running more locally. Now this bears the question, if we have these distributed models right now, can you map them to your local thing? So assume this stuff is already running, and people agree, okay, we want to do this 10 times more efficient. You run it on a single CPU, but we need some kind of translation process to now get this distributed things onto a single machine. Any ideas about this?
First of all, yes, distributed problems of distributed computing are applied for this design absolutely, without any exempts, let's say. I also consider this form of secure multi-party computation is a mechanism to improve performance, exactly. So instead of, let's say, 5 different separate machines, like servers located in different countries, let's say, you have a platform where you upload your binaries, and they represent your original server, and in this local place they can compute much faster and then go back, let's say that. So that's the design in the background. But of course, the problems related to, consensus, very funny, BFT, Raft, and other stuff can be applied and should be, of course. We don't solve this, and we cannot solve this, I think.
Well, it would be interesting if you just press a button and your distributed instance ends up on your CPU in an enclave, and then these 5 guys do the computation locally on a CPU. So that the translation from a distributed case that already exists to one that is then mapped locally to a machine. I believe there's a bit of a framework involved there, but that would be the idea. So very nice implementation.
Okay, thank you. Yes.
So you mentioned before, like you can't stop an enclave, and then at some point maybe you have to all call out. That's not great. When you schedule your actor, do you try to minimize that? So can you schedule in a way that you can keep a small number of cores busy all the time, and then you never have to call out because there's always something, another actor to be scheduled on that core, you know?
Firstly, you can provide some mechanisms for, so the mechanism for setting affinity was exactly for this. So when you want to collocate your code and data within the same core, and if you want to, and if you need a mechanism for scheduling, this mechanism also can be implemented at the assignment level, not inside in the source code. However, it's not the primary approach to solve this problem. I mean, the problem when you need to leave an enclave. The best way I found, it's not a part of the framework, but you need to have, let's say, at some moment when you cannot get a message, you need to leave an enclave manually. But you do this for not random, but let's say statistically identified interval of time. There is nothing better. Oh, I don't know. Thank you.